introduce you. Hi everyone, thanks for coming. Today we have Yuri Nikolayevsky from Trobe University in Melbourne, and he's gonna talk about Einstein hypersurfaces in irreducible symmetric spaces.
Thank you, Ivan, and thank you for, well, kind introduction and also for the invitation to give this talk. And well, this is what I'm going to talk about: Einstein hypersurfaces in irreducible symmetric spaces. And as it said, this is a joint work with my very dear friend and colleague Jeong Hyeong Park, who is already who is also one of the attendees. And let me maybe say a few words before I start showing some slides. Now, of course, Einstein geometry and Einstein manifolds are very extensively studied. There are many open questions, still many conjectures, many everything. They're very extensively studied, a lot of results. There is this classical book on Einstein manifolds and everything. And to some extent, surprisingly, or maybe not surprisingly, but I would say that this extrinsic counterpart of the question, which manifolds are Einstein, are somehow not that well developed. And by this I mean the following. The following question: how to understand and how to classify Einstein submanifolds. So you have some nice space, and the question is, what are Einstein submanifolds of your space? And indeed, well, in such like a broad generality, this doesn't make much sense because really, if you have any manifold Einstein, remaining manifold Einstein or not, you can always embed it to some space, provided your codimension is large enough, like Nash embedding and all that stuff. So you have to impose some restrictions, and as we work in submanifold geometry, restrictions of extrinsic nature. And you can go with the codimension, or you can go with some condition on the second fundamental from, say, totally geodesic or totally umbilical, or canalities, this or that. Or you can, you may want your submanifold to have some extrinsic symmetry, some symmetry inherited from the ambient space, or something like that. And then you have a lot of interesting questions, and Jeong and I asked ourselves probably the first question in this like hierarchy, if you want, of questions: hypersurfaces. So what can you say about Einstein hypersurface? You're given a Riemannian space, and you want to understand its Einstein hypersurfaces. And again, here there is some naive point of view, but which we may always keep in mind when working in this area and on this particular question. Now, if you look at a hypersurface in Riemannian space, say your ambient space has dimension n+1 and your hypersurface has dimension n, the hypersurface is given by one function of n variables, right? And then you impose your Einstein condition, which is n squared on two differential equations. So you get something very, very strongly overdetermined and very restrictive. So in some sense, to some extent, the correct question would be not the one I stated a little earlier, but this one: which Riemannian spaces admit Einstein hypersurfaces? Which Riemannian spaces admit Einstein hypersurfaces? For example, you can ask which homogeneous spaces admit Einstein hypersurfaces, and this is pretty non-trivial question. As we will see a little later in this talk, even some very nice spaces do not. CPM, for example, complex projective space, does not admit Einstein hypersurfaces, and I mean like real Einstein hypersurfaces, right? So let me just stop the ball rolling. Let me look at my first slide, and let me ask the very first question, the very first version of this question. And what if you have just a space of constant curvature, Euclidean space? What are Einstein hypersurfaces in Euclidean space? And as we all may expect, this is known for like centuries and almost literally, because we have this beautiful theorem, which is proved by, I think, independently, but different people. And now this 21 here in the heading, it's not this 21, it's 1921. So we have a space of constant curvature and dimension at least 4. And we have an Einstein hypersurface in this in our space of constant curvature. Now the statement is this: either our hypersurface is totally geodesic or totally umbilical, or of canality 1, or the product of two spheres with Henry curvature in the sphere. Now totally geodesic, well, means totally geodesic. Totally umbilical means, well, totally umbilical, the second shape operator is multiple of the identity. Of canality 1, well, this means that your shape operator has rank 1 at every point, and such submanifolds are more or less, they depend on one variable, on the curve, right? So even probably our students in the second and third year differential geometry, they can see a curve in the 3-dimensional space and then the union of tangent lines to our curve. So this is your typical canality 1 developable submanifold. And
Yuri, sorry, just one more. Can you do you maybe want to make the whole screen, the full screen view?
Okay.
At the moment, it's not.
Right.
I think if you go to view.
Right. Yeah, I said it's Alt L, but
yeah, there should be full screen mode.
Control L. I said that it's Alt L. Right. So, okay. All right. But right, much better. Thank you. Right. So, yeah. Okay. All right. So we have total umbilical and product of two spheres of the same Ricci curvature in the sphere. What is this? Well, this is what it says. You take two spheres, and you have to choose the correct constants, radii and dimensions, to make your thing Einstein. So this is the first result in this direction, and now from this result we can go in different directions. What would be our next candidate, next class of spaces in which we want to understand our Einstein hypersurfaces? And we can go either to reducible spaces made of these spaces of constant curvature, or we can go to general symmetric spaces. And let me show first of all a result about reducible spaces. It's a very recent result. So we have one of these two Riemannian spaces. We multiply a sphere with a round metric by R, or hyperbolic space with a round metric by R again. And the statement, the theorem, said that any Einstein hypersurface in any of these two spaces necessarily has constant curvature, and this was proved in like 2 years ago. And then such surfaces, such hypersurfaces are known. There's hypersurfaces of revolution in such spaces, and hypersurface of revolution is what you think it is. So you take your, say, Hn times R, you take a geodesic in Hn, you take the group which keeps your geodesic pointwise fixed, and then you take the product of your geodesic by your R, you take a curve. This is like a two-dimensional plane. You take a curve there and you add by that group, you get your surface of revolution. And of course, you need to choose a correct curve. So you get some ordinary differential equation, which you can solve, and you have like some family of hypersurfaces depending on some constants. I think not too many constants, right? So this is classified, this is understood, but of course, even if you go a little further in this direction, this is not known, this is open. Say you have a product of two spheres, have different curvature, even of the same curvature, you have just product, like a bunch of spaces of constant curvature, what are Einstein hypersurfaces. Well, my personal expectation would be that they're very rare. Probably it may be that almost no such hypersurfaces. Maybe if you take a product of several copies of hyperbolic space, same Ricci curvature, you get something. But anyway, question is open. And another question, this time we look at irreducible symmetric spaces. And of course, we start with rank 1 symmetric spaces. And here I have the list of those, at least of those which are simply connected. And we have this theorem to which I think 10 people contributed to this theorem. Of course, there were like 6 separate publications, but still 10 people contributed to this complete classification. And now we know that indeed, as we might have expected from the very beginning, Einstein hypersurfaces are very rare. And even in rank 1 symmetric spaces, we have only 2 of them which contain Einstein hypersurfaces. So it's quaternionic projective space and the Cayley projective plane. And in both cases, the corresponding hypersurface is a geodesic sphere of a very particular radius. It's this radius here and this -511, some probably very important constant for the Cayley projective plane, -511, provided we normalize our metric to have the curvature in between quarter and 1. Right. So this is right. This is what we have in rank 1 symmetric spaces, and just by simply looking at the theorem, we may speculate that first, in compact spaces, we would probably expect Einstein hypersurfaces, more Einstein hypersurfaces as opposed to non-compact ones. And secondly, we should probably see geodesic spheres. Now we can now drop this assumption about rank 1 and look at higher rank, and it turns out that both our speculations are just resoundingly incorrect. No and no. It is not true that we have more Einstein hypersurfaces in compact symmetric spaces, and well, probably just neither of them, neither of the existing one are geodesic spheres, maybe in some like degenerate cases. Okay, right. So let me look at the next slide, and here we have the theorem which I wanted to present. So suppose we have a reducible globally symmetric space of rank greater than or equal to 2, and we have a connected Einstein C4 hypersurface. Then 3 cases: either our ambient spaces of non-compact type, and then M is a dimension 1 Einstein solved manifold, or 2 other cases only exist when our space has, our ambient space has dimension 5. So you can treat them like just low dimensional cases. So either you have SU3 by SO3, your solved manifold, Wu manifold, and then your hypersurface must be of canality 2. You have vibration by totally geodesic spheres, and the directrix, the surface which, if you want, governs this vibration, is a so-called special Legendrian two-dimensional surface, 5-dimensional sphere. And every such hypersurface M is in fact locally isometric to the complex projective space of the same Einstein constant as the ambient space. And we have somehow dual statement. So if instead of SU3 by SO3, you will look at SL3 by SO3, then again, your hypersurface, if it is Einstein, must be of canality 2, with the nullity leaves being totally geodesic, this time hyperbolic planes. And now it's directrix, the surface which governs how all these fibers, all totally geodesic fibers, come together in your 4-dimensional hypersurface, is something coming from affine geometry, a proper indefinite affine sphere in the 3-dimensional space. And indeed, the hypersurface itself is locally isometric to CH2, right? So at the very least, it is Einstein. Now, this is and these are if and only if statements, in the sense that any of these surfaces constructed in 2 and 3 are indeed Einstein. Now, I'm fully aware of the fact that I may have been a little, I would say, imprecise about this directrix and everything, and I will explain this construction in 2 and in 3 a little later in precisely in detail. And this has a corollary which says that if we require our hypersurface to be complete, then only the first case is possible. So if you have a complete Einstein C4 hypersurface in an irreducible global symmetric space, then it's necessarily this solved manifold. And the next slides, so almost everything from this point and up to the end of my talk will be sort of introducing and explaining what the words mean in this statement, right? Right, so short comment before I'll go to the next slide. This is about this smoothness condition. So here we require C4. Now, of course, we know that we have this well-known and famous theorem of Kazhdan de Trobe, which tells us that if you have Einstein-Riemannian manifold, then it is analytic. The metric is analytic, always. But of course, this by no means implies that your hypersurface is analytic. You can just take any rectifiable curve multiplied by a line, you get cylinder in the 3-dimensional space, which can be not even C1, right? So, and it turns out that this is not just a theoretic possibility. Indeed, in this case number 3, we may have surfaces of finite smoothness. We may have Einstein hypersurfaces in SL3 by SO3, which are not analytic. Now, in the first 2 cases, they're always analytic. The first one is just subgroup. The second one, we have Legendrian surface, which is given by some complex things, which is minimal and whatever, everything is analytic. Right, so this is the theorem, and let me maybe start going through this statement case by case, and let me introduce each of these classes of hypersurfaces in a little more detail. And are there any questions so far?
Yeah, but probably you'll
Oh, just in there. Okay, wait.
probably you'll pay
Yeah.
attention. You'll pay attention to this later. But I wanted to ask about so the surfaces in 2 and 3 are
Yes.
incomplete, right? And the only thing we're asking,
No.
and the only thing we're asking for from a hypersurface is that it's connected and no other conditions other than it's. We're not asking.
Einstein. Yeah.
Okay, we're not asking to be like properly embedded or something. It's just connected and Einstein, and that's it.
You just connected an Einstein. Yeah.
Okay.
Yeah. So So maybe just some idea which we may have like behind the cases 2 and 3 is indeed this one very simple surface which is made of tangent lines to a curve 3 space. It always just develops bad points on every fiber. So this is what happens here. Right. Okay. All right. So let me look at the next slide. And right. So Einstein's manifolds of codimension 1. What is this? And now here we're going to have a lot of Lie algebra. So we have a symmetric space of non-compact type, and of course we have the Cartan decomposition, and we have the Iwasawa decomposition, and we have our maximal abelian subalgebra, and we have nilpotent n. And we have only semi-direct product of A by n, and this is solvable. And then, of course, at the group level, we have a global diffeomorphism. And the good thing about this is that if we take A times n, this acts simply transitively on M bar on our symmetric space, which in other words just means that M bar is a solvable Lie group with a left invariant metric. And of course, this left invariant metric is the same as the one coming from our decomposition. So if our space is irreducible, then it's Einstein. And so we have a solved manifold, we have a solvable metric, solvable Lie group. And then in addition, it is Einstein, right? Now, what do we do with this? Well, first of all, this Lie algebra, A semi-direct with n, it has a distinguished vector, and that vector lies in A, and this is the mean curvature of the subgroup n, right? So you have your AN, this is your Riemannian manifold, your solid manifold, metric solid manifold. In it, you have your submanifold n, subgroup n, which is a submanifold. That submanifold has mean curvature vector at every point, say the identity, and capital H is this mean curvature vector, right? And it's not hard to compute, and it is known that this vector H can be defined purely algebraically. So we just take any vector A from our abelian part, and then H is such that for any such A, we have this equation here, right? So in the sense, H is just perpendicular to the unimodular ideal of your solvable algebra, right?
What do you mean by the trace of A?
Oh, sorry. Yeah, on the next slide, this is correct, but here, trace of add of A.
Oh, yeah.
Right. Sorry. Yeah, trace of add of A. Right. So, right. So we can just write down our favorite algebra and favorite symmetric space, and very easily compute this vector H. And now here is the construction. We take any non-zero vector psi from A, which is perpendicular to H. H is sacred. We are not allowed to touch it. We take anything which is perpendicular to H, and then we take the orthogonal complement of this psi. And we get a codimension 1 subalgebra, ideal of course, but subalgebra of A semi-direct with n. And now it's going to be subalgebra whose exponent is an Einstein solved manifold of codimension 1. And of course, it's well easy to see that it has the same Einstein constant. It is minimal because in the sense all the mean curvature are still there because we took psi perpendicular to h. And of course, it's not totally geodesic because it is not, because we have this theory about the index of a symmetric space, which is the maximal codimension of minimum codimension of a totally geodesic proper submanifold, and we know that the index is greater than or equal to the rank, and our rank is at least 2, so nothing of codimension 1 may ever be totally geodesic. And why this is so, why it is still Einstein, this is because of this old result of Walter, and let me show this result. And here I have trace of add A, sorry Ivan, for this type on the previous slide. So we are given a metric solvable Lie algebra, n is nilpotent, then radical, A is abelian, well, what acts on n. And the metric is such that A and n are perpendicular, and then the inner product, and then add A acts, of course, by commuting symmetric by commuting derivations of n, but on top of that by symmetric commuting derivation, symmetric with respect to our inner product. And then we define our h as before, but this time with the correct formula. And then we have these formulas which tell us what is the Ricci curvature of our metric solvable Lie group, right? So if we take two vectors from A, the Ricci curvature is given by the right-hand side of the first formula, and the Ricci of an is always 0, and the Ricci of n1, n2 is computed from the Ricci of the nilpotent group n, and something which depends on h, and of course on n1, n2. Now, the beauty of this theorem, if you will, of this lemma, is this. If you have your A semi-direct with n, and you remove from your A a vector which is perpendicular to your h, then the right-hand side do not change at all, right? So trace A1, A2 is still the same, trace add A1 and A2, 0 is 0, and here Ricci n is only something depending on n, and h is still there because we chose psi to be perpendicular to h. So you take a vector which is perpendicular to our h, you take its orthogonal complement, you exponentiate, and you get a subgroup of codimension 1, which is, as a Riemannian submanifold, is hypersurface of codimension 1. And because of this remarkable fact, it is also Einstein, provided the space you started with was Einstein. And by the way, as you can see, we used here irreducibility only for our ambient space to be Einstein. So this construction works always when our ambient space is Einstein. You take any symmetric space of non-compact type and reducible if you want, but Einstein, yeah, with correct scalings. And then the same works perfectly. You can just construct your A, your N. Of course, you will have some, like, there will be like some reducibility, but then you can take your vector in such a way that it's not perpendicular to any of those, or you can take it in some of those. Anyway, this construction still works. And this is our first case. So we have a whole bunch of Einstein solved manifolds of codimension 1, right? And this is what the theorem says in like general dimension case. And let me before discussing other two cases, let me make the following remark. Now, if in general, we have Einstein homogeneous non-compact space, complete Einstein space with negative Einstein constant. There was this long-standing Alexeyevsky conjecture, which was very recently resolved by Ramiro Lafuente and Christoph Bohm, saying that all of them are of this type. So if you have any homogeneous Einstein space with negative Einstein constant, then it is isometric to a semi-direct plus semi-direct n with correctly defined metric with a abelian and nilpotent and so on and so forth. Right. So, for example, there is no Einstein metric on, say, SL3. Right. Right. But anyway, this was our case one, and let me pause for maybe a few minutes. Sorry, for maybe a few seconds, and let me ask: are there any questions so far?
I might have a question about what you just mentioned about the Alexeyevsky conjecture. So maybe I'm just missing something, but I thought the original formulation, which was proved that, so if you have an Einstein manifold, which is, I think it was homogeneous and simply connected, then it was diffeomorphic to Rn. I think that was the with negative curvature.
It is true. Yeah.
Yes.
So this is what they proved, that but there was an earlier paper which said that if it is diffeomorphic to Rn, then it is a solved manifold.
Oh, yeah, that's what I've been missing. Right.
Yeah. Right. So yeah, in general, so if you have like G by H, then you can just from topology, you can more or less get that it must be a solved manifold. Right. Okay. All right. So the next slide, and here again the same theorem which we had 2 slides earlier, and we have the other 2 cases. And let me now try to understand what the other 2 cases tell us. We have SU3 by SO3, or we have SL3 by SO3. 2 cases are similar, they are like parallel, and let me start with treating them simultaneously, and then we will separately look at each of them, concrete constructions in case number 2 and in case number 3. So first of all, we have our Einstein condition, and from some algebra, from some equations, from something, it follows that indeed our Einstein hypersurface must be of canality 2. This means that if you write down the shape operator of your hypersurface, so you have a hypersurface in the space of dimension 5, your hypersurface of dimension 4, you have your shape operator, it has rank 2, right? And then you can prove that it is foliated by 2-dimensional totally geodesic submanifolds of the ambient space. Of course, there are also totally geodesic 2-dimensional submanifolds of your hypersurface itself, but what is more interesting and restrictive, also of the big space, right? And for totally geodesic submanifolds of symmetric space, in some sense they're all known, in some sense they're not, right? So I mean, in principle, there are many constructions like Lie triple systems and everything, or you have this construction with like an antipodal like points. I think it's Chen Nagana, some old result. On the other hand, if you want to like make a list of concrete geodesic submanifold. It turns out that even if you look at the maximal ones, starting from some point becomes quite non-trivial. But luckily for manifolds of dimension 5, everything is known, and you have, say, in SU3 by SO3, you have spheres, you have projective spaces, you have spheres times R, well, times S1, and you have hyperbolic planes, and these two-dimensional total geodesic submanifolds are exactly spheres in SU3 by SO3, totally geodesic two-dimensional spheres, and hyperbolic planes in SO3 by SO3. So what do we do next? We look at the Grassmannian of such totally geodesic submanifolds. So we take SU3 by SO3, or 5-dimensional space. We have some 2-dimensional total geodesic spheres in it. We look at the totality of the universe, the Grassmannian of such spheres, and it turns out that for SU3 by SO3, this Grassmannian is just a sphere SU3 by SU2 in C3. Now, of course, SU3 by SU2 is not our like everyday symmetric space because it is not, but it's a sphere with a round metric, and we have a similar picture, if you want, in the SL3 by SO3 case, except of course your space is pseudo-Riemannian, right? It's a little different, right? And we have some paracomplex structure and so on. And what do we do next? So we need a 4-dimensional hypersurface. We know that it is foliated by 2-dimensional spheres, and these 2-dimensional spheres are parametrized by points of this Grassmannian. So we need to take a 2-dimensional surface in this Grassmannian, and then to every 2-dimensional surface in this Grassmannian, say locally, if everything is fine, there corresponds a 4-dimensional hypersurface. And the question is how we choose this 2-dimensional surface in the Grassmannian so that the resulting 4-dimensional submanifold hypersurface is indeed Einstein. And it turns out that these 2-dimensional surfaces are very well known, and they are sort of, well, famous, very well known. So in the compact case, we have so-called pi-on-2 special Legendrian surfaces in our sphere S5, in R6, which is like C3, which is R6 with a complex structure. And in the non-compact case, we have so-called special paralegendrian surfaces in the parasphere, which correspond to proper affine spheres in the space R3. So if we don't work in paralegendrian or in affine geometry on an everyday basis, this may just look like a collection of words. But on the last slide, or second last slide, we'll look a little closer at this case, and we will see that this is a very nice and very beautiful geometric object. Okay, so this is a construction. You get that your surface is fibered by totally geodesic things, and the totality of this totally geodesic things is a given, is one of 2 known manifolds. And so you take a 2-dimensional surface in the Grassmannian, and it parametrizes your Einstein hypersurface. This is the meaning of the word directrix in the statement of the theorem. This is what directrix means. Right. So, case 2, special Legendrian surfaces. What do we have in this case? So M is SU3 by SO3, and we can of course identify this space with the subset of symmetric matrices in SU3 where this map is Kobayashi embedding, and it's isometric and everything. And then it turns out that the totally geodesic 2 spheres which we are interested in, from which our Einstein hypersurface constructed, a very nice description. So we take an arbitrary unit vector in our or in our R6, and then we need the set of all the matrices from here that is of all symmetric special unitary 3x3 matrices which satisfy this equation. And for every individual vector set, we get a totally geodesic to sphere. Strictly speaking, if we change that to minus z, we get the same to sphere, unless we introduce some orientation and distinguish between same sphere but with the opposite orientation. But anyway, everything, well, this construction is pretty much local and the result is local. So here we don't have to worry too much about this 2-to-1 map. And now we call a surface in the 5-dimensional sphere Legendrian if this vector I z is normal to our surface at any point z, right? So you have a surface, 2-dimensional surface in your sphere, which is a 5-dimensional sphere in C3. You have multiplication by I, which is of course your complex structure, and then your you take the position vector of your of a point on your surface, you add by the complex structure, you get something which is normal to your surface, not only normal to z itself, which is always true, but also to your surface. Right, and then in these Legendrian surfaces, we have a subclass of so-called special, beta special Legendrian. And beta here is a number. It's a number, well, from 0 to pi, or strictly speaking, from this circle, right? So we call such Legendrian, we call a Legendrian surface beta special Legendrian if at any point we have this equation. So the determinant of these three vectors, three complex vectors, is e to the power of ib, where z1, z2 is an orthonormal basis for our tangent space. Now, of course, the determinant is always has modulus 1, so it's always e to the I something real, right? So Legendrian surface is special Legendrian if this something is a constant, right? This number must be a constant. Okay, and then what the theorem which I showed before says, well, you take a regular hypersurface M in SU3 cross SO3, and then if a hypersurface is an open domain on this union where F2 is a pi into special Legendrian surface, then it is Einstein, and the converse is also true. So you take your Einstein, you take your special Legendrian to surface in the sphere, and from it you construct your 4-dimensional Einstein hypersurface, right? And so constructed hypersurface of canality 2, and the nullity leaves are our totally geodesic spheres, and it's locally asymmetric to CP2, and it has the same Einstein constant as M bar, right? So this is the construction, and let me look a little closer at this beta special Legendrian surfaces in the sphere, and we look at the next slide. There are many of such surfaces, and there are different ways of describing them, and one of them which I would like, just my personal favorite, is this one here. So we start with a certain function from R3 to R, just function of three real function of 3 real variables. equals. And we require our function to satisfy two conditions. First of all, our function is too homogeneous, meaning that if you multiply x1, x2, x3 by some lambda, your function is being multiplied by lambda squared, right? And secondly, if you write down the Hessian 3 by 3 matrix of the second derivatives of your function, then the determinant of that matrix equals the trace of the matrix. So beautiful property, two symmetric functions of your matrix are the same. So of course the trace of the Hessian is a Laplacian. Right? But I must say that in reality, the differential equation which you get from these partial differential equations, nonlinear with second order, is highly non-trivial, right? But then, provided you have such a function, capital phi, you can construct this. Very sorry, there is a typo here. It should be I in front. Right. So you take each of your xi's and you take xi plus I, meaning not these I, not 1, 2, 3, but the root of -1, multiplied by d phi by dxi, right? And in this way you get a 3-dimensional cone in your R6y cone because your phi is too homogeneous, right? Be a cone. Then you intersect your cone with the sphere, with the unit sphere, and you get your special Lagrangian surface, and you get what you actually get is 0 special Legendrian surface. So if you want a pi on 2 special Legendrian, you need to just to add by some g with a, say, determinant I, say multiply one of the coordinates by I. The simplest example here is just totally geodesic sphere S2 in S5. It is perfectly special Legendrian, and by the result of Yao, if you have a complete special Legendrian surface which is homomorphic to the sphere, then it is totally geodesic. And you may have many tori, really many tori. Here is the simplest possible torus you can think of, but there are like many of them, and they don't have to be like somehow symmetric or anything. They can have even topology. They can be somehow knotted and still be special Legendrian. So there are many of them. There are many such surfaces. Okay, right. All right. So any questions?
Yeah, I wanted to ask, does this agree with the notion of Legendrian in the contact geometry?
Yes, yeah.
But this notion of, so alpha special Legendrian, where alpha is this number between 0 and pi, okay, is this special to this particular contact manifold, or can it be kind of generalized to other contact manifolds? Because I've never encountered it before.
You mean
not just Legendrian, which is fine, but the alpha special.
Alpha Legendrian, yeah. So yes, and you are asking whether we can have
whether we can define something similar in general in some contact manifold, or is it specific to this particular space?
Oh, I see. Yeah. So right. So you have a contact manifold, right? Oh yeah, I see. It's a good question.
Because this definition of alpha special seems to be using the
it's essentially you're using the contact structure of the sphere on a sphere. Yeah. So you can definitely define something. Well, you can define, but I think you can define Right. Yeah. I'm not sure. Well, I'm not sure it will be very nice geometrically, but definitely you can. I think you can define this for an arbitrary contact manifold. Now, one of the features here, because of the round metric on the sphere, is that special Legendrian they're minimal.
Oh,
In
okay.
general, this is not necessarily true if you just start with an arbitrary contact manifold.
Okay, thank you.
Right. Okay. All right. So I think it's not much time left. So let me look at the last two slides, my presentation, and we have here affine spheres. Now, to be honest with you, I don't want to go in very much detail through this slide, so I will just show it. And in the sense, it's everything which is written here just dual to what we had in the previous slide, but this time we have a parallelogendrian structure. We have, instead of a real vector plus I times another real vector, we have a 3 form and 3 vector, and we have unit sphere, which this time is the set of pairs vector and the 3 form such that, sorry, 3 form, no, 1 form in 3 space, such that our 1 form acts on our vector and gives us a 1, and we get this sphere, and then we have a SL3 action, and more or less it's all the same, except everything is the minus sign, right? In the sense. So we again have totally geodesic, two-dimensional hyperbolic spaces, which can be described similar to how we described our two-dimensional total geodesic spheres, and the description is here. We take those matrices from SL3 by SO3, which satisfy certain equation, the dual to which can be considered as the equation x times z equals z bar, which we saw in the previous slide, and so on and so forth. So, right. Now, one good thing about all this stuff is that from parallelogendrian geometry, you can very easily get to something very, very, very familiar, to geometry in 3-dimensional space, to differential geometry in R3. And the idea here that you again have your 2-dimensional surface, which lies in R3 times R3 star, whatever. And at all good points, you can just project your 2-dimensional surface to the first factor, to R3. And what you get down the bottom after you project it uniquely determines for you your original surface, provided it was parallel Lagrangian, right? So in the end, you arrive at just 2-dimensional surface in a 3-dimensional space. But that 3-dimensional space has no inner product, no metric. It's affine space, only affine. More precisely, it's equiaffine. So we have linear space R3. We have like a flat connection, just usual connection, parallel translation of vectors from one point to another, just what we know from primary school. And then we have the volume density, which is just unit volume, which is invariant relative to the group which preserves like parallel translation, right? So we have we have volume form, we have so we have the determinant, we have we have parallel translation, but we don't have metric. Then we can define something which is called proper indefinite affine sphere, and this was firstly introduced by George Tsitseika, I think, in the early 19th century, and the formal definition requires us to go too deep into affine geometry. We need certain Blaschke normals to pass through the same point in R3. And Blaschka normal is something which replaces the usual normal when you have no metric. And the definition is, it's not immediate. So I will not probably show it here on this slide, but what you can do, you can just introduce any metric in your space, and then it turns out that this condition, proper, indefinite, affine, sphere of center, affine, curvature -1 in equiaffine space, is equivalent to that. So you have a certain surface, two-dimensional surface in three-dimensional space. You compute its Gaussian curvature, you compute its normal, you write down this, and it's -1. And this, it turns out that this is equiaffine invariant. So if you change your metric to some other metric with the same volume element, your surface will still satisfy this equation. Although here we obviously have some metric things like Gaussian curvature and the unit normal, still this turns out to be an affine invariant. And what we have on the left, this is this central affine curvature -1. So this -1, it's this guy here. Okay. Right. So we have this, this equation, and another possible way of visualize these surfaces is similar to the one which we had in the compact case. So we again start with a function in R3, real function of 3 variables. And we want our function to be too homogeneous, and we again have a nonlinear elliptic, not necessarily, no, non-elliptic equation on our Hessian. And then we take intersection with the unit sphere, and we get one of those surfaces. And let me just show you my last slide, and I will stop there. So the simplest example of such a surface is just the hyperboloid x1 squared plus x2 squared minus x3 squared, just hyperboloid of one sheet. You have a lot of ruled examples. So you take an arbitrary curve in R3, you parameterize it in such a way that this thing is a 1, and then you have this ruled example. But notice this, we have gamma prime plus u gamma, not gamma plus u gamma prime, gamma prime plus u gamma. And this is where, if you remember at the very start, we discussed the smoothness. This is where non-smoothness, not analyticity may come from. You can take for your curve something which is just C2, C3 for sure, just to be on the very safe side. Your curve doesn't have to be analytic, and then you run all your construction, you get non-analytic Einstein hypersurface. And the second simple example is this beautiful cubic surface here, the hexagon hat. So also this is how it looks. We have x3 multiplied by x1 squared plus x2 squared, and the right-hand side is just scaled in the way that we have the correct number. And just to finish my talk, another example of the hexagon hat. This. So this is how it looks in the real world. And thank you for your attention. I think I'll stop here.
All right. Thanks a lot, Yuri.
Thank you.
Does anyone have any questions?
Hello, yes. Hi. I would like to ask you a question, because I'm very curious about the part that you didn't explain here, which is how do you arrive at these examples? How can you analyze the Einstein condition when in a space, in a symmetric space where you don't have explicit formula for the curvature tensor? So I mean, for instance, in the classical result in the complex projective space, you have an explicit formula for the curvature tensor of the CPN, right? And this is very, I think, helps a lot in order to do some manifold geometry in complex projective spaces. But now, if you forget about complex and quaternionic projective spaces, even if you go to the Cayley projective space or in the non-compact setting, in higher rank, I don't know of any explicit formula for the curvature tensor apart from the curvature, the formula in terms of Lie brackets, of course, not this.
Yes.
But apart from this, we don't have an explicit formula in terms of complex structures, inner product, etc. So how can you manage the deal with the Einstein condition in such a general setting?
Well, yes, you are very correct. Yeah, it was a lot of work, and of course we had only this general formula with triple bracket x bracket y bracket z. So the only thing which, well, the thing which I would say saved us, which helped us a lot, is the fact that Einstein condition is very overdetermined. So even knowing not very much about the structure of the curvature tensor without knowing any complex structure, well, quaternionic structure, whatever, even without knowing much, you can extract a lot from this condition. And this is one thing. Another thing is this: your curvature tensor is parallel, right? So if you write down to your Gauss equation, you have your curvature tensor, and you have your something on the right hand side, and then you can differentiate that, and you have a guaranteed zero at some correct place.
The Gauss equation, you mean?
Yes.
Okay.
Yes. Yeah. So right, and then even without knowing your curvature tensor, you get a lot of algebraic conditions on your hypersurface. So to start with, just directly from the Gauss equation, you get this condition which is called curvature adapted.
Sorry?
So curvature adapted.
Yes.
Adapted.
Okay.
Right. So just directly from that, and so you have some eigenspaces, already you have some like eigenvectors and everything, they nicely agree. And then you start differentiating your curvature tensor up there, and you know that the derivative is zero. And because of that, you get some extra algebraic equations without derivatives. You get some number of them. And then from all these algebra, you eventually you eventually get to some simple case, to some manageable cases. Yeah.
But can you, at the beginning of the proof, show that an Einstein hypersurface must be curvature adapted? Because are these examples curvature adapted?
Yes, they're all curvature adapted.
Yeah,
it is curvature adapted. It is curvature adapted, which is more or less just follows from the fact that your ambient space is Einstein, your hypersurface is Einstein, and the Gauss equation.
Okay.
So you write down your Gauss equation, you just
very good, very interesting. Yeah. I have a slightly different question, maybe not so different, but if you have a guess why we don't have examples in the complex projective spaces, and we do have examples in the quaternionic and Cayley cases. Heuristic idea, if you have an idea of this.
Yeah. Right. No, you have like in HPN you have 3 complex structures. Hard to say. Well, yeah. Don't know.
No, okay, okay.
Okay.
It's just
Yeah,
calculations.
It's just calculations.
It's just
Yeah,
okay. What's naturally arrives
it's
when you
not immediately.
Do I get it right that one can probably, in a simpler fashion, show that if there were such an example in CP2 or CH2, it must then it would necessarily be a geodesic sphere, and one just need to kind of find an equation on the radius, and then it later turns out that such a radius exists for H and O, but does not exist to C for C for some reason.
Yeah. This could be, this
Then
could be,
mysterious why it doesn't exist for C then.
this could be possibly a reason, because the last step in all these proofs, when you have this geodesic sphere, is this: you have your curvature adapted surface, hypersurface. You take the normal, you take a normal geodesic at your point, and you look at the you look at what at the second variation. You just move your point along your every point of your surface along the normal geodesic by some particular distance, by r, and then you write down your Jacobi equations, and you find that it collapses in all directions simultaneously. And so this tells you that if you take your hypersurface and take all your normal geodesic and you just walk from your surface by that particular distance, all the points come to a single point. So originally you're on the sphere. So it may be that in these other cases, something doesn't work with this construction. It may be that you have to move in the opposite directions or something, or different distances, possibly. But with full honesty, I don't know the correct heuristics behind that.
Okay.
Yeah.
Well, maybe if I can pose a last question related to curvature adaptiveness. Maybe I'm wrong, but I think there is a result by Jürgen Bert in the quaternionic projective space that says if you have a curvature adapted hypersurface in HPN, I think, then it is homogeneous, and it is one of the following examples. Do you think that your techniques can be applied to try to get similar results in more generality in the compact setting, probably? I mean, yeah, you said that the curvature adapted condition played an important role, so maybe it's strong enough to provide classifications.
This is very possible. So I think definitely for the Cayley projective plane, we can replace Einsteinity, which implies curvature adaptedness, by just being curvature adapted, and then we might have some classification which may contain these ones, this geodesic sphere. So now, of course, all the geodesic spheres are homogeneous because you have all these stationary subgroup which acts on it. But yeah, so yes. So in reality, this Einstein hypersurface condition, at least in this context, is a particular case of curvature adaptedness condition. But there are some other things to Einsteinity which help us. But say for OP2, I'm pretty sure you can very definitely try to go some distance, maybe to get a full classification.
Okay, thank you very much. Thank you very much.
Thank you.
Can I also ask one small question?
Yeah.
So you mentioned that the construction, in the first case, for where you're in the non-compact type, and then you take a solvable subgroup of AN, you mentioned that the construction itself works if your space is reducible, but it's still Einstein, so that the normalizing constants kind of agree.
Yes.
But do I get it right that the classification result itself, that these are the only three cases, does require necessarily that the space is irreducible?
Yes, yes.
Uh-huh.
It may be that something similar is still true when we have a reducible case, but I simply don't know.
Okay.
Yeah, so we use irreducibility a lot, like in root decomposition, roots and all the stuff. So yeah, we need
I see.
for the proof.
Okay, great. Thank you.
Yeah.